Okay, hello. In class on Wednesday, we spent a long time, half an hour or something like that, proving the Euclidean Division Algorithm. What is the Euclidean Division Algorithm? It says that given any integers, a and b not 0, you can divide a by b. That's integer division, and when you do that, b is going to go into a certain number of times, plus there's going to be some kind of remainder. And you can keep finding b's in A until your remainder is pretty small, specifically less than b. So more precisely, the theorem says that there exists a pair of integers, q and r, such that given any a and b, that q and r are in this relationship, and also that r is small, that the size of r is less than b. And okay, b could be negative, which is why we have to use absolute values, but if b is positive, which is more typical, then we just say that the remainder is less than b. Alright, so, and we discussed in class how there are sort of an infinite number of pairs, q and r, that are going to be in this relationship. After all, this is just kind of a linear equation. So if you give me a and b, I can find an infinite number of q's and r's, but we feel that only one of them will have an r which is less than b. Okay, so great. So did we finish in class? Kind of. What we did was the hard part, and the hard part was existence. We showed that there exists a pair of numbers q and r that meet these two requirements. And you know what we did was we considered all possible remainders. So all possible numbers r of the form a minus qb, where r is positive. So we put all the possible positive remainders into a big set, and we applied the well-ordering principle to that set. And thus we focused on the smallest remainder from that set, and we showed that that smallest remainder is a remainder which is less than b. So, all right, I'll put a check next to this, yeah, that was the hard part. Now, what's left is uniqueness, because after all, the sort of extra kind of strength of this theorem is not just that you can find a q and an r, but that there is a single unique way to do this. And okay, we're going to prove uniqueness now. It's going to take 5 minutes or something like that. And okay, yeah, it's sort of one of those things that is just extremely obvious. I'm looking again at the example that we have. It was this one. This was kind of our example. We divided 22 by 5, and we said that 22 is q5 plus. Well, what did we do? We divided 22 by 5. Of course, it's going to. Well, okay. I guess I can write it like this. 22 is going to be some number of 5s plus some kind of remainder. But of course, what's the actual answer? The answer is that it's going to go in 4 times plus some remainder, and that remainder is 2. Okay, well, keeping this kind of thing in mind, then it's almost like just silly. Of course there's going to be only one unique way of doing this. How could there possibly be 2 pairs of numbers q and r, and in both cases that the remainder would be less than b? In this case, b is 5. In other words, this is sort of, I think, just very, very obviously true. That there's really only one. I guess the way of thinking about it is, once you give me r, q is determined. And so to say that I have a pair of numbers q and r and another pair of numbers q and r satisfying this theorem, you might as well just be telling me that you have 2 different r's. But there can't be 2 different remainders, both of which are less than b. That's kind of the idea. Okay, so how do we actually rigorously prove this? Well, we can just do a little, we make a little argument now. We suppose that this actually can be done in 2 different ways. So we suppose that a can be written as some number of b's, let's call it q2, and with remainder R2, and that A can also be written as Q3 times B plus some remainder R3. And in both cases, we want that this R is less than B. So R is less than B, and this R3 is also less than B. Okay, and it's not exactly a proof by contradiction that I'm going to do right now, because I'm not going to actually suppose that it's kind of like a proof by contradiction, but instead of supposing that there are two distinct ways of doing this and showing that that leads to a contradiction, instead I'll just suppose that I have two ways, and then I'll show that those ways kind of must be the same. Okay, where do I go from here? Sorry, I have some kind of sketchy stuff everywhere. Okay, so why Q2 and Q3? No reason. I think I just got this from the book because Q1 came up as a symbol in the previous part of the proof. Okay, well, a couple things. Well, okay, so what are we going to do? Let's begin the argument. I haven't really done anything yet, so let's set them equal to each other, which I can of course do. So I get that Q2b plus R2 is Q3b plus R3, and yeah, now I'm just gonna like do some algebra or something. So what do I get? I get b Q2 minus Q3 and equals R3 minus R2. I think I did that right. Sure. And yeah, so sort of now what? Where is this going? Well, okay. First of all, I find this idea that b might be negative kind of very distracting. So I'm just going to limit myself to the case where b is positive, and I promise you that you're losing sort of nothing of the proof by only looking at the b is positive case. The b is negative. The b is negative. Its negative case is exactly the same. And okay, now let's go. Well, all right. The thing is, again, I sort of am annoyed by this idea of not knowing sort of which of these is positive and negative. So, well, I'll also, I guess this is kind of another case here, is that I'll say, without loss of generality, let R3 be bigger than R2. Okay, and in fact, I should say greater than or equal to, because I'm not actually assuming that they're different. And so, look, if you have these, two remainders, one of them's got to be bigger, or they have to be the same. So either R3 is greater than or equal to R2, or R2 is greater than or equal to R3. Okay, finally, now we can just kind of like begin. What I want to say now is something which is just extremely obviously true. And maybe I should have said this even 3 minutes ago. Look, if you have these two remainders, and they're positive, and they're each less than b, then if I have two things that are less than b, then of course their difference is less than b. Alright, that's sort of so obvious that in the textbook he doesn't even prove that, he just immediately asserts it. But okay, I feel like we should maybe do that, so let's do it now. How can this be shown? Well, the way I did it was to say, alright, look, I have that R3 is less than b, and here I drop the absolute value because I'm only considering the case where b is positive. Also, it's true that that R2 is positive, and or greater than or equal to 0. And so now I'm going to add b to both sides of this, so that gives me b is less than or equal to R2 plus b. And now I'm going to sort of take these two facts and stick them together, which is to say that R3 is less than b, which is in turn less than or equal to R2 plus b. And what have I accomplished? That by a sort of kind of a transitivity now, if R3 is less than b, which is less than or equal to R2 plus b, then actually I have that R3 is less than R2 plus b. And so R3 minus R2 is less than B. Okay, so that's exactly the thing that I said was extremely obvious. If you have two things that are less than B, then of course their difference is less than B. And here I'm avoiding all the annoying, I want to do this whole problem without any annoying absolute values. And so, okay, great. So what? Yeah, oh, and of course also, well, okay, here, I'll just continue up. So what do I have right now? The argument kind of continues up here, which is I've shown that this R3 minus R2 is less than B, but also, of course, this is going to be greater than or equal to 0 because I've assumed that R3 is the bigger one. And now I am ready to bring in this. So I just come right here now and I take this relationship and, well, what do I get? I get then that 0 is less than or equal to, in place of R3 minus R2, I put B, Q2 minus Q3 is less than B. And now that's the inequality I wanted. If I divide all three sides of that inequality by B, which I'm certainly entitled to do, then I get that Q2 minus Q3 is less than 1. But alright, in other words, if the difference in these remainders is less than B, then if this right-hand side is less than B, this is the talkie version, then the left-hand side must be less than B. But how could this left-hand side be less than B? Because this left-hand side is B times something. And therefore, we've concluded right here with this something, the difference in the quotients being a integer, of course, because Q2 and Q3 are integers. But I don't know too many integers which are greater than or equal to 0, but also less than 1. In fact, the conclusion that we can draw from this is that since nothing is between 0 and 1, no integers are, that actually Q2 minus Q3 just must be 0. And so Q2 is Q3. And that's it, because if Q2 and Q3 are equal, then of course that makes R2 and R3 equal also. And so starting with the idea that there were two different, I didn't specifically say different, but that there were two ways to do this, satisfying the theorem, we've shown that in fact there's really just one way. Okay, that was like very tedious and low level. I think this was still sort of like, in some sense this was like a very short, very easy argument. There's really like kind of one line of algebra. If you're very smart or experienced, you might find this to be very easy, almost obvious. You might also find this to be kind of very hard. I don't find this kind of math, this kind of math doesn't kind of come very naturally to me personally. But I do think this is a kind of skill that you need to get good at. So if you're not good at it already, I think with some practice, this sort of thing becomes more accessible. These kinds of low-level manipulations with absolute values. This is not what this whole course is going to be like, but we are going to do a lot of this sort of in the first month to get good at it. But yeah, just to repeat, I started with a pair of Q and R satisfying the theorem. I set them equal to each other. I just did some factoring to focus on the difference between the remainders and the difference between the quotients, simplifying things a little bit by only focusing on positive B values, and simplifying things further by only treating the case where R3 is the bigger remainder. We showed that if the two remainders are each less than B, then their difference must be less than B. And if their difference is less than B, then this left-hand side is less than B. And the only way for that to be true is if the difference in the quotients is 0. And so that's it. Okay, goodbye.